everybody for attending today's session, FEA Simulation. It doesn't have to be difficult. And I'll be co-presenting today with my friend and colleague Kendred. And without further ado, let's just take a quick look at what we'll be covering today. Today's session should last somewhere around 40-45 minutes if all goes to plan. Quick introduction here, but FEA for design engineers, looking at what are the products and capabilities, just kind of a high-level overview, looking at the FEA workflow, and then I'll hand over to Kendred, and he'll take us through the demo portion, looking at the importance of considering nonlinear behaviors when making design decisions, etc., all the way through to doing some fatigue analysis. So you can read the words as well as I can, but hopefully you get the gist of what we're going to be doing today, and there's no surprises there. So I just wanted to kick off here with what we mean by doing upfront simulation in the design and development process, because I believe that's a really key aspect of what Hageman and company delivers to customers. And if we consider this triangle as representing the universal space of anybody that might want to do simulation, the very top part of that triangle, we have the sim analysts, simulation analysts or specialists. These are people that have set out on a career of full-time simulation. They perhaps have a high-level master's degree or a PhD, and every single hour of every single day they're doing simulation analysis. We believe, though, that most of the most return for investment is delivered early in the process. So if you can do some relatively appropriately, I don't want to say simple, but that's the word that just came, so I'm struggling for my words a bit, but if you do some what-if studies early in the process, you get maximum return on investment, and we call that upfront. So it's for design engineers, generalist product people that maybe are multitasking, but definitely multi-talented. These are products that fit in that space have to be easy to learn, easy to use, and easy to do design optimization studies with, like I mentioned, doing what-if scenarios. And so the products that are available today sort of fit in that category from the Autodesk products that Hageman promotes and supports. It's Inventor Professional, and I'm pretty sure everybody on the call will know about that. By the way, that just uses some technology that Autodesk acquired maybe 10 years ago from a company called Placitech Technology. Really great FEA technology, and it's what provides you with the basic linear static stress analysis that lies within Inventor. And then Nastran In-CAD. And Nastran In-CAD is a product that really takes it to the next stage. So we've got, and that uses Nastran technology. I'll explain what that is in a second or two. We have a third product called Simulation Mechanical, also uses the same Nastran technology. And that really is more intended for people that are using Pro-E, people that want to do things like pressure vessel analysis. There's a lot of overlap between Nastran In-CAD and Sim Mechanical. But the easiest way to explain it is if you are a SolidWorks user or an Inventor user, 90% of anybody that falls into those two products from a CAD perspective that wants to do any kind of FEA analysis will find Nastran In-CAD to be a great tool. If you're doing some of those sort of pressure vessel special type analyses and you don't use SolidWorks and Nastran In-CAD, Inventor, then Sim Mechanical could be a good solution for you. Where does Nastran come from? Well, it basically helped NASA put man on the moon. During the 60s, there was a program, as we know, to put man on the moon, and as part of that, there were actually quite a number of different NASA divisions developing their own FEA codes. All of that was centralized in a region. They produced an amazing platform of technology. NASA, and not a commercial organization, so that software public domain. It was released in 1971, and a number of companies got access to that or have taken access of that domain, that source code. And Autodesk is one of those companies, and so now Autodesk is able to offer inside of a Nastran right within CAD, and that's what the name means, Nastran within CAD. Who's it for? It's for, as I mentioned earlier, it's for the design engineer, somebody seeking directional input or validation during the early phase of their design process. You're using plastics, metals or composites, creating products with moderate to complex assemblies, You need more extended mechanical capability than what Inventor FEA offers, such as nonlinear analysis, thermal analysis, buckling, vibration, fatigue and durability. And we'll expand on, Kendrick's going to expand on a few of those things in a second or two. It does work, as I've tried to indicate here, it works right within Inventor, right within SolidWorks. Again, you'll see Kendrick illustrate that. If you happen to have a mixed CAD environment of Inventor and SolidWorks, the same single license of Nastran In-CAD will work with both CAD products. So in short, if you had one Inventor and one SolidWorks, you don't have to have two separate Nastran In-CAD licenses. The one license can be shared between both products. The workflow, you start with geometry. You basically tell the solver what the parts are made out of, so we assign the materials. We tell the solver how this geometry is going to be used, the operating conditions, and then we get an answer out of it. Once we've got an answer, we can go back and play some what-if games. So maybe now I change the geometry based on that result and interpreting of that result, and now I get another answer. Rerun the analysis and take another model iteration, I get another answer. And this allows us to optimize and innovate on our designs and so on. And we can change materials, change the operating conditions. And very quickly, we get a whole load of different design comparisons, which allows us to focus on the best designs. So imagine we're trying to create, we've got sort of ideas around 10 different designs, but we're a little unsure as to which one's the best performing design. We have our 10 designs, we run them iteratively like this through an FEA solver, something like Nastran In-CAD. We get different answers out, and based on those answers we can determine which ones have the best chance of seeing success. So very quick intro for us today. Most of us are on this call because they actually want to see the product in action. At this point, let's hand over to Kendrick and he can take it from here.
Thank you, Martin. Greetings, everyone. Let me just go ahead and get my screen displayed real quick. Okay, so starting out today, we're going to look at the capabilities that are inside both Inventor Professional as well as Nastran In-CAD, and we're going to run a comparison of the two in a sense. So starting out with Inventor Pro, you've got two main types of FEA that it can perform. The first one being linear statics and the second one being normal mode and frequency analysis. So with the linear statics, it's capable of doing just that, linear static stress, no nonlinear stress. And then of course on the normal mode, the natural frequencies such as what's experienced by a tuning fork, getting the natural frequencies of a material or a mechanism. So if we look at what is behind a linear stress, just to make sure everybody has a clear understanding of this, when you plot the amount of stress versus the amount of deformation of a material. For example, if we start at 0 in the lower left, we apply 100 pounds, plot the amount of deformation or strain, and it deforms 1 inch. Okay, then we plot another point of applying 100 more pounds, so now we're total 200, deforms another inch, total of 2 inches of deformation, 300, 3 inches, 400, 4 inches, you see the pattern. As you plot those lines on a graph, it forms a linear straight line, hence the name linear analysis. When you look at something like a nonlinear FEA, just about every material on the planet is nonlinear beyond some point. And most materials have a linear region. Now that linear region could be larger for some materials like metals, steel, iron, brass, things of that nature, or smaller for other materials such as plastics, wood, glass, things like that. So in a nonlinear analysis, plotting the entire material strength of that material, plotting the entire curve, you get beyond that linear region and you're not necessarily into a failure region per se, but you get close to that failure region. And that's where the behaviors of the material can get a lot more unpredictable by linear standards. So when you're working with a nonlinear material such as plastics or polymers or composites, you need to step outside that box of a linear analysis. So in that scenario, Inventor is not going to fit the bill. You're looking at only linear static loading conditions, static being it does not change over time. So how does this contrast to what Nastran can deliver? Comparing the two side by side, on the left, pretty much equal check boxes. What Inventor has and can do, Nastran can do. On the right is where we see the big difference. Martin mentioned earlier running inside of SolidWorks. That's one of the benefits of Nastran. We have a lot of engineering firms out there that will run multiple packages based on their customers, so Nastran is able to run inside SolidWorks and satisfy that need. Some of the other things that come inside of Nastran, such as welded contacts, surface contacts with friction, heat transfer, linear structural for fatigue, impact testing, nonlinear structural. A lot of benefits of Nastran over what comes in Inventor FEA. Looking at that in a graphical and pretty picture standpoint, you see a lot of this type of analysis being done more and more, as Martin mentioned, not by your PEs and your analytical gurus sitting back in the corner, but now more by the design engineers. And the reason that's happening is because the software has changed and turned to where it's easier to use and more automated. We're pulling from material libraries, we're pulling Young's modulus, Poisson's ratio, we're pulling all of that information from a database, so it's taking more off of the user and semi-automating the process to make it easier to use. So inside Nastran, we can do the linear statics in the normal modes, buckling, the pressure and static and normal modes of an object, linear steady-state heat transfer, analyzing composites, assembly modeling with contacts for linear and nonlinear, thermal stress analysis, nonlinear statics. So we got a lot more stuff we can do here. One of the big ones on this slide that a lot of customers ask for is the very last one, the impact and drop testing. So if you're carrying a cell phone, it has undergone some form of impact analysis or drop testing analysis in some computer software somewhere. So we're getting into that more and more, especially in the consumer products division. How is this going to stand up? You know, children's toys. A lot of children's toys are being impact analyzed to see if they're going to break when the kid slings it across the room. So let's take a look at both of these in action. So jumping over into Inventor, I've got a standard run-of-the-mill plastic table that you go out and buy at Lowe's, Home Depot, whoever. Sits out in your yard, set some drinks on. And with this particular piece of geometry, just to show you the thickness of this, the uniform thickness of this, is 1/4 inch. Pretty easy term for each of us to relate to and quantify. Looking at the material properties itself, standard run-of-the-mill ABS plastic. When I look at the physical characteristics of this property, or of this material, the strength property, the yield strength is right around 2,900 psi. So we're going to apply some loading conditions and see how close to that yield strength we get. So starting out with Inventor Pro, going to my Environments tab and just create a stress analysis. I'll create a single study. And even though I've already got the material specified, if I neglect to specify or if I want to change that material, I can change that assignment here. It pulls the ABS plastic assignment from the material properties, but I have access to change it to whatever other material I wish. I'll go ahead and run with the ABS for this. So the first thing I need to do is set up some operating conditions, and this is going to be the case with any FEA package you run with. So the first thing I need to determine is how is this thing fixed? How is it constrained or positioned in the real world? First and foremost, it's set down on the ground, patio, ground level, grass, whatever. So the first thing I will do is I will constrain the bottom of the feet just by picking these 4 surfaces. Once I have the constraint applied, then I can start looking at the loading condition. So I'm going to apply a force to this central part of the surface on the top. Now the whole idea behind this is a small little plastic table. A lot of times these are used as step stools, step ladders, even little kids getting up there and just standing on them, playing in the yard. So we need to see if this thing is going to break, because essentially somebody's life may not be completely at risk. There is risk of injury if they stand on top of this. So let's see how it's going to stand up to a certain load. And I'm going to make sure and pick a good heavy load because I want a lot of confidence in this design. So I'm going to put 300 pounds standing on top of this. You can choose to specify gravity as well. If you're ever in doubt in your design, if gravity has an effect, you always apply gravity. For this one, I'm just going to tweak the mesh settings and look at the mesh to see how it's coming together and dividing up the geometry into the different elements. That's the whole key of where FEA comes in, is it breaks up your geometry into these finite measurable elements that the math actually is ran on these elements and the points of the elements. So I can look, and I've got a fairly fine mesh, especially on the area of my loading. I've got a nice dense mesh, and the denser the mesh, the simulation can run a little bit longer. The more coarse, the simulation would be faster. The trade-off is the accuracy of the predictability of the simulation. So with a coarse mesh, your results may not be as accurate, but with a fine mesh, you're sacrificing a little bit of time for the simulation to run, but you're getting more accurate results. So I've got my mesh identified, I've got my constraints, I've got my loading. The last step is to actually run the simulation. This takes just a few seconds, pretty quick. You'll see, all in all, take a couple of sips of coffee and you're done. You've got your results. What we're going to look at is 3 key factors. We're going to look at the von Mises stress, how much stress the material is encountering, and keep in mind our yield is 2,900. We're also going to look at deformation and safety factor violations. So looking at the von Mises, we're at 5,000 psi, and if you remember 2,900 for our ABS, we've exceeded that limit. I'll turn off the mesh view and make this a little bit more clear. Obviously here red is bad based on the chart. Depending on your situation, your materials, red does not always mean bad. Red is just the highest level of stress your part is encountering. That red could still be well within your yield strength. But in this case, red is absolutely bad. It's almost 2 times our yield. So let's go ahead and look. We've got 5,000 psi on the von Mises. On the displacement, this thing is flexing 1.3 inches. Visualize that in front of you. That's a large movement downward for a piece of material, even plastic. That's a lot of travel distance. So just that amount of distance alone makes me nervous. This table might not hold up. If I look at the safety factor, yeah, we're not even at a safety factor of 1. We're at 0.57. So right now it's not looking too good. Let's go ahead and compare this. We've ran it in Inventor Pro. Let's see what Nastran gives us. So I'll finish my Inventor Pro simulation, jump into the Nastran In-CAD solver, and the first thing you'll notice is I never left Inventor. I just went to another tab, loaded the environment into Inventor. You've got familiar interface, familiar background, familiar tools that you're working with. Step 1, I've already done this in Inventor. I can take those loading conditions and constraint conditions and just import them into Nastran, or I can create them from scratch in case you bypass Inventor Pro altogether. So what I'm going to do is I'll just input them. You'll notice over in the tree that I get my forces and my contacts automatically loaded and applied. They are translated over. My material did not change, so we're running same constraint conditions, same loading conditions, same material and material properties. The only thing that's changing really is the solver. I do need to make one addition to this, and that is in the mesh settings. I'll change to make a finer mesh just like I did in Inventor. Before we get to that, though, there's two ways you could run this in Nastran. You could run it based on the geometry itself, and it looks at the inner and outer surfaces of the geometry, or you could run kind of a what could be considered a mid-plane analysis. So since this is uniform thickness of 1/4 inch, you could run a shell iteration or an idealization and specify it's only 1/4 inch thick, ABS plastic, just change the color of my mesh, and associate it with all of this geometry. So what it will do is it will run that analysis. Make sure I get everything in here. It will run that analysis based on that geometry, and it defines basically a midplane of the inner and outer faces or inner and outer walls of the geometry. The benefit of doing that is the results are pretty much the same as if you do it to the geometry, and it's faster simulation time. So your results are just as accurate and you're saving time. So I've got my idealization specified, tweak my mesh settings, go ahead and generate my mesh so that we can see that. If you remember, the Inventor Pro mesh was very fine, especially in the area where we're applying the load. I expect to see the same thing here with Nastran. The mesh shape might be a little different, but we're still dealing with a very fine mesh on that inner area where we've got the loading condition. So once we've got the shell idealization specified, we've got our mesh settings tweaked, the next step to do is simply run the analysis and look at the results. You'll notice how fast the solver is. Now we're running two different solvers. In Inventor Pro we had the Plazotech engine, and Nastran we have the Nastran solver engine. What you're going to see is the two different engines yield almost identical results. So we know the math is right on both aspects, no matter which one we use. The solver runs pretty quick, takes about 30 to 40 seconds, and we get our results. You have a status window over the side so you can see how things are running through, what sort of calculations are coming through, how it's looking at the data, how it's looking at the geometry. It also flags and shows any kind of errors or failures, so it's a nice status feedback window letting you know how the solver is running. The solver is complete. I can look at my von Mises results and run a comparison. So we're looking at about 4,800, 4,900 PSI. That's really close to what Inventor Pro said. Looking at the displacement, we were at 1.3 inches in Inventor Pro, and now we're about 1.18. So split the difference. We're averaging 1.25 inches either way we go, whether we use Inventor Pro or whether we use Nastran. Let's look at the safety factor. Inventor Pro predicted 0.57. We're at 0.6. So both solvers are telling me, yeah, this is not a very confident design. It's got some weak area. It's going to break. It doesn't have a good life. But there's an issue. In Inventor Pro, I'm using ABS plastic. That's a nonlinear material. Inventor Pro does not run nonlinear analyses. It's linear only. When I switched over to Nastran, I did the same thing. ABS plastic, nonlinear material, and I made a mistake and did not run a nonlinear analysis. I ran it as a linear analysis. So both tests were the wrong test to do, but they gave me the same results. So at least I've got repeatability between the two engines. So I've got my confidence. So let's change it. Let's go from a linear analysis and run it as a nonlinear. Here's how easy that is. the analysis already run. I made the mistake, so let's come in here and let's edit the analysis type. You'll notice we ran it as a linear static. Here's all the different analysis types we can run in Nastran. I'm just going to scroll down through here and pick nonlinear static. It is that easy. Choose the nonlinear static. Have a couple of things I need to set up. On my nonlinear setup, I'm going to change the number of iterations that I run. So it was running as 10 iterations. That's going to take a little longer. I'm going to shorten this down to 5. Basically what you're telling it is you're taking that loading situation and you're dividing it up. So with increments of 5, I'm going to divide that 300 pounds into 5. The first loading application is going to be 1/5 of the 300 applications, 2/5, and it runs the analysis on each one of those increments, and it builds all the way up until it applies the entire 300 pounds. Running 10 iterations just takes longer. So I'll say OK. I don't need to change my constraints or my loads or my mesh. Everything's already done. Simply changing that setup and then rerunning the analysis. So this one actually takes the longest to run. While that's running, discuss a couple of things that we found here. Get back through. And what we did was we ran 2 linear FEA studies, one in Inventor Pro, one in Nastran. That was the wrong study to run in both packages, but it told us with identical loads, identical support situations, and the same material in both applications, Inventor Pro gave us the displacement of 1.3 inches, Nastran 1.18. That's why I said split the difference, 1.25 inches. Von Mises running about 5,000 PSI in Inventor Pro, about 4,900 PSI in Nastran. Pretty much the same PSI. Safety factor violations about the same, 0.57 versus 0.6. So we made the mistake and ran it as the wrong analysis, but we're getting the same results. So when we run it as a nonlinear analysis using the right algorithm to accurately predict the stress, what kind of material changes might we need to make? What kind of design changes might we need to make? Is nonlinear going to give us the same results? If it is, we definitely need to make some changes. Thicker material, that's always an option. We're already dealing with a 1/4 inch thick plastic. That's a lot of plastic. That's a lot of wasted material. Could we sacrifice the material, thin it down, and maybe reinforce it with some ribs? When you go with thicker material, obviously you've got more material cost. You also have increased tooling cost when you're dealing with something like plastic. You've got to change the molding situation. When you run with thicker material, you also have a risk of voids and pockets, gas voids, and seam lines in that material. All of that's going to come together to make it weaker. The ribs could actually reinforce it. You could run a thinner material, apply some ribs. Your material cost may or may not change, may even go down a little bit. When you do something like ribs, you are going to have an addition to making a mold change. Again, you could have increased costs, maybe, maybe not. Or do we look at using a different material altogether, a higher strength plastic? Maybe even retool this and don't run as a plastic, run as some other composite material. All of that can come together to give us different results, maybe a stronger table or even a weaker table. Maybe we're going in the wrong direction. So when we run a study, why do we run it as nonlinear? First and foremost, when you're dealing with a large flat surface and a concentrated load at the center of that surface is not going to behave in a linear fashion. It's going to have some nonlinear behaviors to it as it deforms and stretches. Nonlinear study specifically applies the load a little bit at a time, whereas a linear study is just a thud. It applies the load and that's it. You don't get any kind of gradual introduction of the load. So with a nonlinear study, maybe we don't hit the 300 pounds, but maybe we hit 260. Is that good enough? The deformation that comes back from a nonlinear study actually can be turned around and fed into the analysis because it can analyze and compensate when material deforms. Sometimes it gets stronger. Case in point, hex head bolts, cap head bolts and screws. Most of those are formed through a cold forge process, and by doing so, they're actually changing the grain structure of the material when they form the head of that bolt. By doing that, it actually increases the strength of the bolt. The same thing can happen with a lot of other materials. Plastic is actually one of them. Linear studies also don't incorporate that deformation or stiffness into their matrix like the nonlinear does. And lastly, we're dealing with ABS plastic. So it is by nature a nonlinear material. So I don't know if you heard that or not while I was talking. There was a ding. That ding either means the computer has finished the simulation or the apple pie is done. So let's get over here and look and see which one it is. Yep. Nope, simulation. All right, so when I look at these simulation results, bring it up side by side so you can see it good. I'm going to look at the von Mises stress. I have my different load increments. If I can look at 5%, or 20%, 40%, 60%. I'm going to go and look at 100% of the loading. I want to see the worst case scenario. So when I display those results, remember the linear analyses told us around 4,900 or 5,100 psi. The nonlinear is right at 2,900. We're right there at our yield point of the plastic material. So we're actually on the right track. This design's looking pretty good so far. Granted, I still don't want to be that close to it, so I might want to still incorporate a few ribs to get some more strength and lower that stress. Let's look at the amount of deformation. When I switched to deformation, we were displacing over an inch, averaging 1.25 inches. We're now displacing right at 5/8 of an inch. So we've cut it in half. That seems a lot more expected. 5/8 of an inch, yeah, that's still a good bit of movement, but nowhere near like over an inch. That's what I would expect it to see happen to it when somebody stands on it or when a child sits on it. Lastly, let's look at our safety factor. We were at 0.57 and 0.6 respectively for Pro and Nastran running a linear. Now we run it as a nonlinear and we see we're right at safety factor of 1, almost. So as we put in the ribs, that's probably going to climb. I'd rather see a safety factor of approaching 10, 15, maybe even 20 if I can squeeze that out of the design. And the ribs are probably going to get that for me. So we can see that, yeah, we started out with the wrong analysis. Then we changed to do the correct analysis, and our design actually has a lot more confidence, or we have more confidence in the design that it's going to work as is. Might still need to beef it up some. But let's go one step further. What is the overall lifespan of this design going to be? One of the biggest things we get asked for with Inventor Pro is, can we test for fatigue? And in Inventor Professional, you cannot. You cannot test for the life of a component or the product. But in Nastran, you can. All we have to do is simply change the analysis type, moving from nonlinear static down to a multi-axial fatigue. We do have a few things to tweak when we do a fatigue analysis. We have some conditions that we need to set up. First and foremost, on the fatigue setup itself, we're going to have it run for von Mises stress, for the stress life. Next, we're going to look at the loading condition. Now, this is critical. In the loading condition, we're not just going to drop 300 pounds and just let it go and let it sit there with a static load on it. We're going to apply the 300 pounds, take the 300 pounds off, apply it again, take it off, and we're going to just back and forth, like somebody stepping up, stepping down. Maybe they're using it as an exercise stepper. See how far they get with this thing. So when you're working with a loading situation like that, we're just going to build a simple load table. And the way the load table works is at time of 0, our load is going to be 0. At halfway through the cycle, make sure point that out, 0.5, halfway through the cycle, our load will be fully applied, 300 pounds. At the completion of the cycle, the load goes back to 0. So to show what this looks like on a graph makes more sense. Starting out with a loading of nothing, applying up to 300 pounds, taking the 300 pounds off. Repeat. Load of nothing, apply 300, take off. Just repeat that cycle over and over. The next thing we have to do once we have our loading conditions specified is we have to tell our material, here's your behaviors under a fatigue analysis. So in the material itself, we actually come in and just apply specific data for the fatigue. Now, you can get this information out of a lot of material spec catalogs, material information books. MatWeb has all this stuff on there. You just plug in the numbers based on whatever material or submaterial you're running with. So on this particular ABS plastic, we'll specify the slope. Then we will specify the amount of stress for the material. The number of cycles, I'm going to run it with 1,000 cycles. The K factor, I'm going to skip because with the K factor, it's an endurance limit. The way we're going to be running the software is going to tell us that endurance limit based on our material conditions. And then with the secondary slope, this is normally near 0, if not 0. And then lastly, material finish, corrosion resistance, other factors like that that could either strengthen or weaken the material. Again, all of this data is available at MatWeb and other resources like that. Looking at the XY plot of it, you can see as the curve comes down, as it goes through its life, the stress that gets applied is actually going to weaken the material as it goes through the cycles. So the more cycles we do, that material is expected to get weaker. Once all of that is done, I simply run the analysis. No change to the mesh or anything like that. That doesn't take very long to run, so while that's running, I got one last slide to throw at you, and that is looking at this condition. We've been working with ABS plastic. Let's look, for example, at something like a low carbon steel, the stress and strain curve. Pretty much every material on the planet is going to have a stress and strain curve that somewhat mimics what you're seeing here. This is kind of a generalized case, so there are differences. And most materials will have a linear zone, at which point you can apply the load, it deflects, you take the load off, it returns to its normal zone or normal behavior and normal shape. Number one, you've got your ultimate strength where everything fails. At that point, it's not going to return to its normal shape. The predictions get kind of wild on what's going to happen to the material. Number two is the yield. That's where it will no longer return to that shape, and it goes into more of the stress hardening region, which we'll get to in a second. The third is your failure point. That's your break point where all your material is going to break apart and completely fail. No way to put it back together or return it to its original shape or original behaviors or strength. The strain hardening region, that's the region I was talking to you about with things like hex head bolts and cap head screws, how that head shape is formed from a cold forge process. That can actually, depending on the material, can harden the material and strengthen it. That's why that curve will sometimes rise up to give more strength. And then in the fifth area, all materials have a necking region. Basic explanation of this, if you ever take a long piece of taffy and start to pull a piece off to give to your child or your spouse or your dog, the taffy starts to neck and get thinner. That's the taffy failing and getting ready to break. So every material falls into this situation pretty much. And the plastics, the metals, they're all going to follow a similar flow. So back here looking at the fatigue, let's see how much fatigue we can get out of this, how much endurance we can get. The simulation is done. I can look at the life contour, and when it loads the weather map, it shows areas of red. These are going to be your bad areas. These are going to be your lower life expectancy areas. So as somebody stepping on and stepping off of this, your weak area is pretty much this entire top. But you'll notice areas of blue, that pretty well indicates infinite life. The legs aren't really encountering much stress at all, especially down at the bottom. So they're going to be the only things left after somebody steps on and steps off of this table repeatedly. You can animate the results of the life contour to see how this life expectancy starts small on the tabletop and then grows to encompass more area. Not that the entire top is going to break, but the entire top will eventually start to see all that stress and get weaker with time. The last contour is the damage contour. This gives you your localized region or localized area of damage. So as you press your foot on there, really the surface of the table that contacts your foot is getting some reinforcement from your foot. So right under your foot is not necessarily going to break, but right around the outer edges, there's your weak areas, and that's what the outline is showing here. When this material breaks, it's going to break in those areas. And it shows you how, as that load is first applied at the start of the cycle, through the 50th cycle, the 100th, the 500th, the 1000th cycle, this is the area that it's going to break at. So this allows us to see, okay, our displacement looks pretty good, our stress is, yeah, we're close, we need some ribs, and our safety factor tells us we need some ribs. This also tells us we need some ribs. We need to strengthen this up and change the design a little bit to give it a longer life, not just more strength and resiliency, but a longer life. And with that, I will turn it back over to Martin.
Good, very much appreciate that. All right, let's make myself presenter here. So hopefully that gave you a fairly high level but somewhat detailed look at some of the capabilities of Nastran In-CAD. And just to stress, that is really just a few. We're scratching the surface in sort of 40 or 45 minutes that we're taking here. There's a lot of stuff under the hood, as Kendra showed with those slides where there's he went through, I think there was 4 or 6 on each page, so tons of capability in the software. But hopefully you got a feel for the ease of use, the fact it's embedded in Inventor and or SolidWorks, and so it's a very familiar interface to you. How much does Nastran cost? Just in spirit of transparency here with you guys, it's $3,500. I think I already mentioned it's a single user floating license. I mean site-wide, works with Inventor and SolidWorks, and that's a term or annual pricing. $3,500. So our ask, this kind of wraps up today's session, but our ask is that if there's been anything at all of interest or that resonates with you, we'd love to do a live demo on one of your products. All you need to do is send us your model. We'll use this to actually show how Nastran In-CAD can be applicable to the things that you're involved with, the products and parts that you care about. And let's partner together. So all you need to do is just send me an email. If you've got any technical questions or commercial questions, feel free to copy or send them to myself and Kendra, and we'd love to work with you on that. If you've got any additional feedback for improvement, for things you'd like to see in future webinars, again, just feel free to contact us. And with that, I will hand back to Ashley, and she can formally end the presentation for us. Thank you.